Hello and welcome to Lab 5. This lab was a lab about Faraday's law. We sent a magnet through an aluminum foil and observed what happened after. First, we'll go over an introduction, some key ideas, a setup, some physics principle, an experiment, the glow script code, and then finally a conclusion with some final questions. The objective of this lab, again, was to obtain a visual understanding of Faraday's law by observing a magnet fall through a roll of aluminum foil. The magnet, being a source of a magnetic field, would then produce a current in the foil as it fell through it, that in turn, the current would then produce a counter-magnetic field that exerts some force on this magnet. Some of the physics principles that we wanted to use in our observation or Ohm's law, Faraday's law, as mentioned previously, Lenz's law, and then flux and momentum. We have some formulas over here in the bottom left. The bottom one we used in the last lab, and the top three are Faraday's law, Lenz's law, and Ohm's law. We'll get into the experiment, some setup and procedures, but the result that we got was an experimental time of 0.696 seconds and a computational time through glow script of 0.662 seconds. Just a quick touch on that. Our procedure and setup, you can see on the right in this diagram, was in a roll of aluminum foil of which we dropped a magnet through it. Magnet had a magnetic dipole moment U. The aluminum foil had a width of foil of 0.6 centimeters. The length of the tube was 0.32 meters. We had the mass of the magnet, and then we also had later the radius of the tube. Using the magnetometer app on our phone, we were able to ascertain the layout of the magnet and label the poles, and we were then able to drop it through an aluminum tube 5 separate times, scrub the video footage to identify the lower bound and the upper bound of the time, and then the difference between the initial and final gave us the total time falling through the tube. And we took a 5 number average. Next is the glow script. Above you see some constants, a graph that we are plotting that you'll see at the end, velocity versus time. And we just put in a bunch of the constants and some measurements to begin with: length, width, radius of the tube, etc. All the rest was given through this code. We then created the graphic of the aluminum tube and it would display the magnet going through the tube as the graph is populating. Next, we created the bar magnet in the script. You can see it all right here. We used, this was from lab 3. We used the same data. This was also from lab 3, creating the dipole moment. And then lower, we created the simulation loop, as you can see here. Then we calculated, we knew a certain period of time would, if only gravity was interacting with the magnet, we knew that the magnet would fall at this speed. And since the speed that we were measuring was different than that, we were able to identify some external force acting on it other than gravity and treated that as the magnetic force acting on the magnet from the current. And the current was induced by the magnet. And you can see that right here, F net equals F gravity plus F magnetic. Keep doing that, I'm sorry. And then here was our output. As you can see, the velocity versus time graph goes like this. And again, you can see our experimental time of 0.696 is actually pretty close to our computational time of 0.662 seconds. And question 1, what if the resistivity of the conductor was reduced as close as possible to 0? How would the fall change? The braking force would increase to a point where it balances the gravitational force and prevents falling, aka levitation. What if holes or slots were cut into the tube? How would this impact the current? This would have disrupted the natural flow of current, causing the brake force to be less strong than originally, and the magnet would then fall faster as gravity has a larger percentage of the force on it. Some sources of error obviously are other magnetic fields that we weren't taking into consideration. We assumed that only gravity and this magnet were acting on the aluminum foil. And that'll be it. Thank you for stopping by.